what I have to do is to move on to chapter 12 in the book, which it's titled Alcohols from Carbonyl Compounds. And the first thing that this book does is to remind you of the types of carbonyl compounds that are known. So these are the types of carbonyl compounds that are very common. Every one of them has a particular feature, and that feature is C double bond O. And if you have a carbon, which can be aliphatic, methyl, ethyl, propyl, etc., or aromatic, benzene ring, substituted benzene ring, and naphthalene, you have a carbon and a hydrogen, it's called an aldehyde. And you know a few things about aldehyde, because you know these things come far left of the NMR spectrum, 9 and 10. If you have two carbons, they can both be the same, or they can both be, or they can be different. They can be aliphatic, methyl, ethyl, propyl, cyclohexyl, etc. Or one or both of them can be a benzene ring or an aromatic compound. You've got two of them, ketone. This is a substance called acetone. This is a substance called formaldehyde, used for preserving dead bodies. This is an acid. Again, this can be aliphatic, methyl, ethyl, propyl, and so on, or aromatic. This one you put on French fries. It's acetic acid. This is an ester. Again, these can be any types of carbon. That's ethyl acetate. Some people use that as nail varnish remover. It's not a good idea, it dries out the nails. Well, in an emergency, you're going out tonight, you've got a lab session, you can't go home, you realise you want to change the colour. You can use it, but don't do it too frequently. This is an amide. R can be carbon or hydrogen. And here, actually, this can also be hydrogen or carbon. This can't be hydrogen because it decomposes. If one of these is hydrogen, you've got an aldehyde. So those are the different types of carbonyl compounds. And now you know something about what's called the electronegativity of oxygen and carbon. You know that oxygen is more electronegative than carbon. And what that means is, in a bond between oxygen and carbon, the oxygen tends to suck the electron density towards it. So bonds like this are generally polarized in this way. So there's a little plus charge on the carbon and a little bit of negative charge on the oxygen. Now that tells you something. If I just clean the board. If you've got a part of a molecule that is deficient in electron density, let's just write up some generalized structure like this. If there's a slight buildup of positive charge on the carbon, you know that a nucleophile, in other words, something with a pair of electrons, will be quite willing to do that. because nucleophiles have an electron pair and they like to attack a part of a molecule that's deficient in electron density. Equally, a part of a molecule that's deficient in electron density basically goes around saying, please attack me, especially when it sees a nucleophile. So that's one concept you need to get in your mind, that something with a pair of electrons will attack the carbon of a carbonyl group. The next thing that you need to get in your mind is that since you now know about alcohols, and I've just told you about carbonyl compounds, and you know from last term about hydrocarbons, you obviously must realize that there is a series of compounds in which you start with carbon attached only to hydrogen, then you go to carbon attached to hydrogen and one oxygen, then you go to, by single bonds, to carbon attached to hydrogen and to oxygen by a double bond, and then you go to carbon attached to more than one oxygen. So you have a series of compounds. So let me just write that series down for you. Let's say that we start with a hydrocarbon, and by some process we convert it to a substance that's got one OH group, so we have an alcohol, and by some process we convert that to an aldehyde, and by some process we convert that to an acid, and by some process we take this carbon, we really treat this quite brutally, and we get CO2. Now, the concept that I'm trying to introduce to you is the business of oxidation states of carbon. The highest oxidation state is this thing. The lowest oxidation state is this. So when we go from here to here, we're oxidizing the compound. When we go from here to here, we're oxidizing the previous compound, that one. When we go from here to here, we're oxidizing that substance. When we go from here to here, we're oxidizing this material. So the more oxygens you have on a particular carbon, the more oxidized that carbon is. That's how we talk about it. Now, it doesn't have to be oxygen. What it has to be is some element that's more electronegative than carbon. And so, if you take this compound and do something to it and end up with CO2, we say we're oxidizing. Likewise, you know that oxidation is the reverse of reduction. If you start with this and go to here, you're reducing this carbon. If you go from here to here, you're reducing this carbon. If you go from here to here, you're reducing that carbon. And if you go from here to here, you're reducing that carbon. So I just want you to have in mind that, that concept. Now that you've got that concept in your mind, I know the textbook actually assigns numbers. Forget about it. When I was reading this part of the textbook this morning while I was having my orange juice and porridge, with raisins and cinnamon, scrambled eggs on toast, and coffee, cheese. While I was reading that, I was, honestly. It's not easy to get good, high-quality domestic help, but I'm feeling the cook that I have now, it's superb. It's superb. I hope they've given me better than dry bread for lunch, which I brought in today. When I was reading this chapter this morning, I noticed that the book gives numbers it allows you to assign numbers to the oxidation state. Well, I've never used these numbers in my life, so I don't think you need to know about that. All you need to know is if you take a hydrocarbon and replace one of the OH bonds by oxygen, you've done an oxidation. And if you then remove two hydrogens from this, again you've done an oxidation, and if you replace a hydrogen by another oxygen, you've oxidized further, and so on. If you go the other way, you're doing a reduction. Now, apparently, what you're going to do this week in the lab is to, I think, you're going to make alcohols by reducing carbonyl compounds. It was last week, was it? Okay, they're out of phase. Now, what I want you to tell you now is how to reduce carbonyl compounds to alcohols. And from what I've just been saying, obviously, there are different types of carbonyl compounds. And so it won't come as any surprise for you to know that there are different reagents used to reduce a carbonyl compound depending on what your carbonyl compound is and how far you want to reduce the compound. For example, if you've got a carboxylic acid or an ester, you may want to reduce it all the way down to an alcohol, or you may want to reduce it only down to an aldehyde. So there are a few things that we need to know about that. The first thing that I want to tell you about is the use of lithium aluminum hydride. It behaves as though it is a hydride source, and it is a very powerful reducing agent. So it will reduce almost any carbonyl compound. And if you take a carboxylic acid, for example, let's take this one. And you add LAH, that's the normal abbreviation. What you will get is a primary alcohol. And if you take an ester, let's take this methyl ester and treat it with LAH, you now get two alcohols. Again, from the carbonyl portion, you get a primary alcohol. The other alcohol you get is this part. So what I need to tell you now is, how does this happen? What's actually going on? Well, the book gives some mechanism that I think is a little too detailed, and it also indicates the stoichiometry. In other words, how many lithium aluminum hydride molecules do you need to reduce one molecule of an acid or one molecule of an ester down to the alcohol level. I'm not going to go into such enormous detail. I don't think you need to know it, but what you do need to know is how these products arise. Now, I said at the beginning that LAH behaves as though it is a hydride ion. And I told you earlier today that a carbonyl group is polarized so that the carbon bears a bit of a plus charge, and therefore a nucleophile will attack the carbon. So that's the basic information that you need. So let's use that information to understand how a carboxylic acid is reduced. Let's use the same carboxylic acid. Now, there's one other piece of information you need. I said we would use a carboxylic acid, and the word acid means that that substance is willing to give up a proton. And if you treat a proton source with a hydride ion, what happens is this. So the first thing that you get when you add LAH to an acid is you get hydrogen and the salt of the acid. There's nothing funny about the salts of acid. If you look on the packages of prepared foods that you can get in the local supermarket, you'll see that there are sodium salts of various acids present, sodium benzoate, for example. We've all eaten some of these sorts of acids. Now the next thing that happens is that a hydride will attack that. So now we have we've used up 2 hydrides. Now I'm going to put an M there in a circle and an M there in a circle, and the M just stands for metal, which could be aluminium or lithium. And what happens next is that electrons come back and expels one of those pieces. So now we've generated in the flask an aldehyde. But this aldehyde is in the presence of more hydride ion. The hydride ion goes in there. And now we get that. And if we add acidic water, we will generate the primary alcohol. So when you reduce a carboxylic acid with lithium aluminum hydride, the first thing that happens is the acidic proton is removed. You get bubbling and hydrogen comes off. And you get some salt, whether it's a lithium salt or an aluminium salt, it doesn't matter. And that salt has a carbonyl group in it. The carbonyl carbon is then attacked by hydride. Now you get a species that expels one of the oxygens. And by doing that, it generates a new carbonyl group. But that carbonyl group is in the presence of hydride ions provided by the LAH. And so the carbonyl group of the aldehyde is again attacked, not again, is attacked by hydride to give you now an alkoxide. An alkoxide. You've heard of ethoxide, sodium ethoxide. You've heard of sodium methoxide. Those are, in general, alkoxides. They're just the salts of an alcohol. And if you treat this with HCl, you will protonate this and get lithium chloride and aluminium chloride out of it. So that's how you reduce an acid. Now, how do you reduce an ester? Again, using lithium aluminum hydride. So let me clean the board and show you how you do an ester. Notice what you get from an ester. You get the alcohol from this piece, and you get that alcohol. So I want to show you, I'll write this up again, but I want to show you how to understand how all that happens.
So I kept looking for a
So there I've taken, in general, an ester. I've taken a methyl ester, but I could have taken the ethyl ester, or the opal ester, or the phenyl ester, all sorts of esters. And I've treated the ester with hydride from lithium aluminum hydride. Now you notice that when I did reduction of an acid, the first thing that happened was that the acid proton was removed to give hydrogen. But if I have an ester, I don't have an acidic proton, and so you don't get hydrogen coming off. All that happens is that the hydride attacks the carbonyl to give you a tetrahedral intermediate. In other words, the carbonyl carbon is now attached by single bonds to 4 different things, and you know when carbon is attached by single bonds to 4 different things, the carbon atom is tetrahedral. So people frequently refer to this as tetrahedral intermediate. And this now ejects this part of the ester to give methoxide ion, which on acidification will give methanol, and it also generates an aldehyde. Let me write this aldehyde a little more neatly. It generates an aldehyde, and the aldehyde has a carbonyl. The carbonyl will be attacked by hydride ion in the normal way to give an alkoxide, which is this, which on acidification now gives you a primary alcohol. So from an acid and an ester, from the carbonyl part, you get a primary alcohol. From an ester, from this part, you get whatever that alcohol is. If this is Me, it's a primary alcohol. But if the ester were this, you get that alcohol, which is a secondary. And if you had another methyl group there, you get a tertiary alcohol. So in all these cases, you get a primary alcohol. Now, maybe I ought to explain to you, what do we mean by a primary alcohol? We mean that the hydroxyl group is on carbon that's attached directly to only one other carbon, which is here. What do we mean by a secondary alcohol? We mean the hydroxyl group is attached to carbon that's attached directly to 2 other carbons, this one and this one. And what do we mean by tertiary alcohol? Well, we mean that the hydroxyl group is attached to carbon that's directly attached to 3 other carbons. So that's the story for lithium aluminum hydride. It will react with carboxylic acid. It's a very strong reducing agent. It reduces almost all carbonyl compounds. And the carbonyl compounds I want to tell you about today are acids and esters. And it reduces those down to alcohols. And from the carbonyl portion of esters, you get a primary alcohol. And from the other part of the ester, you get whatever the alcohol is. And from the carboxylic acid, you get a primary alcohol. There is another reducing agent called sodium borohydride.
So there's a reducing agent? Yep. I would like to do that. Thursday already. So I don't want to do it. It was really easy. A lot easier than the last time.
God, we're almost done. So
I know.
close.
We want to do that. We'll eat
And sodium borohydride is also a source of hydride ion. But sodium borohydride is a much weaker reducing agent than lithium aluminum hydride. And sodium borohydride is almost always used to reduce only aldehydes and ketones. So if you take this aldehyde and you treat it with sodium borohydride, frequently done in alcohol, you'll get a primary alcohol. And if you take a ketone and do the same thing, you will get a secondary alcohol. And all that's happened in both of those cases is that a hydride is added to the carbonyl compound. And you'll notice that sodium borohydride is used in an alcohol. You cannot use lithium aluminum hydride in an alcohol because it reacts very vigorously. Sodium borohydride reacts very slowly with alcohols. And so it turns out that that is a good solvent for doing sodium borohydride reactions. Sodium borohydride is a much safer reagent. I've seen quite a few fires with lithium aluminum hydride. I've never yet seen a fire with sodium borohydride. Now we won't worry about the fact that sodium borohydride has 4 hydrides on it. We won't worry about that. We will just regard sodium borohydride as a hydride source. And in fact, sodium borohydride, one molecule of it can provide 4 hydrides. And lithium aluminum hydride, likewise, one molecule can provide 4 hydrides. But we don't, organic chemists don't tend to worry about the so-called stoichiometry. Now, what you should try is the problem number 12.3. So I've told you now about the preparation of alcohols by reduction of carbonyl compounds, reduction of acids and esters with LAH, and reduction of aldehydes and ketones with sodium borohydride. You can reduce an aldehyde and ketone with lithium aluminum hydride, but that's sort of overkill. You can use a milder reagent, and the milder reagent is sodium borohydride. What I want to tell you about now is going the other way. If you have an alcohol, can you oxidize it up to an aldehyde? Or can you oxidize an alcohol to a ketone? And in the case of the aldehyde, can you oxidize it further to a carboxylic acid? So let's deal with that.
But then I have to control you that way. Animal fighting.
They're so cute.
They are very cute.
I've never actually had a scarecrow.
Scary.
Scary.
That's true. It was like funny. It was like really after
Yeah.
What happened to him? I haven't seen him in a while.
I still have it. Maybe a different day.
you take chromium trioxide, that's this compound, which we will write like this, and you mix it with pyridine and HCl, you can get this substance as a solid, which is called pyridinium chlorochromate. Chromate, or PCC for short. And PCC oxidizes primary alcohols to aldehydes. If you have a primary alcohol, PCC in dichloromethane, you can get an aldehyde. And if you have a secondary alcohol, and you treat it with PCC in dichloromethane, oops, sorry, you get a ketone. So now we're going the other way from what I was talking about before. I was talking about reduction. You take a ketone, you reduce the sodium borohydride to get the secondary alcohol. But if you take a secondary alcohol and oxidize with PCC, you get ketone. If you take an aldehyde, reduce it with sodium borohydride or LAH, you get a primary alcohol. But if you take a primary alcohol, you can oxidize it up to the aldehyde. And on Wednesday, we'll talk about other oxidation